Okay, in this section we're going to talk about linear geometry. And what we mean by that really is vectors. I'm hoping that you have some background with vectors before. In that case, this is a review. To get some intuition about vectors, we're going to start out with lines in 2 dimensions. And it's very important to understand this simple example because many of the general properties of vectors in higher dimensions work exactly the same way that they do in 2 dimensions. All right, so let's move on here. Okay. All right, now, we know that if we have an equation with 2 unknowns, you can draw it as a line. Y equals mx plus b. All right, suppose we have a system of 2 equations. That means 2 lines. And if we want both equations to be satisfied, that means we're looking for all of the points that are in the intersection of those 2 lines. Now, if you play around with 2 lines in a plane, you find there are 3 possible ways that those 2 lines can intersect. They can intersect in a single point, as here. They cannot intersect at all, as here, or they can intersect in an infinite number of points. Okay. This behavior is very similar to the behavior in higher dimensions, and we'll talk about that later. Okay. So it's good to keep this example in mind. Okay. Let's go and talk about vectors in space. A vector is considered as an object with a magnitude and a direction. It's often represented as an arrow. Vectors can, for instance, model displacements. They can model velocities as well. You see this picture? So these different arrows represent displacements. In some sense, the displacement is the same for each of these arrows. The only difference is the starting point. But we call all of these arrows as representing the same vector because we're focusing on the magnitude and the direction of the displacement in this case. Okay. Now, the notation for vectors, if we think of the vector that corresponds to the displacement from point A1, A2 to point B1, B2, we represent that as a pair of numbers, and it's represented down here. Here's my point A1, A2 down here, and here's my point B1, B2 up here. The displacement is the arrow joining the 2 points. And we denote this vector as a pair. The first number in the pair is the x distance. The second number in the pair is the y distance. And this vector here could represent 1, 2. 1, 2 means over 1 up 2, which is kind of, if you eyeball it, that's kind of what this vector looks like. Okay, so simple representation of vectors and how they correspond to displacement. Okay, so again, we repeat that point that the vector from A1, A2 to B1, B2 is represented as a pair of numbers, and each component is the difference between the 2 corresponding coordinates. Okay, so we have that. So we picture a vector often as starting at the origin, as in this case. So in fact, we can represent the points in a plane in 2 ways. We can think about them as a pair of numbers, as you did in high school when you plotted points on a Cartesian plane. Or we can think of points in the plane as a set of vectors. We can associate each point in the plane with the vector that goes from 0 to that point. These same definitions work in higher dimensions. If I have a higher dimensional space, an n-dimensional space, instead of having 2 components in my list, I'm going to have n components, and each component gives the difference between the corresponding coordinate. Okay? And here, just as before, we're not too careful about distinguishing between a point and the vector which ends at that point. So we can think of the set of n-dimensional points as a set of vectors. We can think of each point and identify each point with the arrow that goes from the origin to that point. Just like this picture I have here, only think about higher dimensions. Okay. Now, what can you do with vectors? First, you can multiply vectors by a number. If I start with this vector and I scale it up by 3, we denote that as 3v, so here's the scaled up version of v. I could multiply this vector by a negative number, such as -1. That's going to reverse the direction and also multiply the magnitude by the corresponding magnitude. So in this case, -v is a vector in the reverse direction with the same magnitude. We can also add vectors head to tail. I'm assuming this is familiar to you. They call this the parallelogram rule. You can think of this as you've got a vector v, a vector w. To get the sum, you take this vector w and you transport it along here so that the tail of w meets with the head of v, and the result here can be thought of as the diagonal of a parallelogram. Okay. So let's think of lines in terms of vectors. Now, we're used to specifying lines using 2 points. We also use the point slope formula in high school, but it's also possible to think of a line as determined by 2 points. Now, if you look at this picture shows a vector from the origin to one of these points, and that's the point 1, 2. The point 1, 2 is represented here. And he also has a vector along the line. Now notice that if I take this vector from 1, 2 and then add any multiple of this vector here, it's still going to be on the line. If I go from 0 to 1, 2, and then I go twice this vector, it's still going to be on the line. If I go 3 times, it's still going to be on the line. No matter how many times, if I go negative once, I'll go out here and go -1. Okay. So that's expressed by this formula here. I go out 1, 2, which corresponds to me going out along this line. And then I go any multiple of this vector. You can see this vector is 2, 1, because I go over 2 and down 1. All right, so this is called a parametric representation of this line, because t is a parameter, t is an arbitrary real number, such that any value of t will give me a different point on the line. Okay. Now, so this vector here is called the direction vector because obviously that determines the direction of the line. Lines in higher dimensions work exactly the same way, which is kind of a neat thing. Okay. Now, what about planes? Now, when you have a line, you know that you can only move in one direction. A plane is a 2-dimensional object, so you can actually move in 2 directions. So here's an example of an equation that determines a plane. And you have to think that this is the same sort of thing. This 1, 0, 5, if I attempt to draw a 3-dimensional set of axes here, attempt to do it. Okay. And 1, 0, 5, if this is my x and this is my y and this is my z. I'm not going to be very good at this, but x would be 1, y would be 0, y would be 5. That would be a point something like this. Draw the dotted line to show. Okay. And if I go out to this point, if I go out to this point and then go any multiple of this distance plus any multiple of this distance, if you think about it, what I'll be doing is defining points in a plane that passes through that point. Okay. I go out to this point, and then I could go any multiple of this distance plus any multiple of this distance. No matter if I just restrict myself to these 2 vectors, to these 2 directions, then I will always lie in this same plane. Okay. Now, in general, we're generalizing this. It's the same idea. It looks a little complicated with all the indices, but really it's the same idea. In n-dimensional space, whenever you go out a point and then add some linear combination of a set of fixed vectors, and that's going to give you what we call a linear surface or linear subspace. If there are k of these vectors, this is a k-dimensional subspace. And you can think about the two examples we've done to see why. If I have one vector with one parameter, then I'm going to get a line. If I have two vectors with two parameters, I'm going to get a plane. It's hard to imagine, but if I have three vectors in four-dimensional space, that's going to determine what you can call a three-space, or he's calling a three-dimensional linear surface. Many ways to call it. But you're always going to get some kind of linear space by taking a point and some linear combination of vectors. Okay. Now let's talk about length and angle. We've already had some idea about the length of a vector, but let's formalize that. And we know intuitively that vectors correspond to directions, and different directions have angles between them. So let's formalize these definitions. Okay. Length of a vector is the square root of the sum of the squares. So this is just Pythagorean theorem on steroids, right? If I've got 3 dimensions, got my 3-dimensional thing here. Whoops, sorry. Don't know why it's doing that. Okay. And I've got a point out here. Don't know why it's doing that. Let me see if I can fix this. Okay. I've got a point out here somewhere. And this is going to have some kind of z component. Not working well for me today. Let's try it again. It's going to have some kind of z component and a y component and an x component. So I could draw it here. It's going to have 3 components. And you know that the distance from the origin to here, it's the sum of squares of these 3 distances. It's this distance squared plus this distance squared plus this distance squared. So pardon my poor picture, but think about the Pythagorean theorem in 2 dimensions, right? And just try to extend that in your mind to higher numbers of dimensions. Okay. Now, if I take any vector v and I divide it by its length, that's like scaling away the length of the vector. And this vector is going to have length 1. Okay. You can do that as an exercise. If I take this vector and I form this quantity, I'm going to get the value 1. Okay. Angle. To find the angle, there's this operation called the dot product. If I have 2 vectors and each vector it has n components, then the dot product is the sum of the product of corresponding components. And here's an example. Notice that the dot product of 2 vectors is not a vector, it's a scalar. Scalar means ordinary real number. Okay. The dot product of a vector with itself, if you work out the formula, just turns out to be the square of the length of the vector. Okay. A triangle inequality says that the length of the sum of 2 vectors is less than or equal to the sum of the lengths of the 2 vectors. Okay, here's the standard picture of that. The sum of vectors goes directly from start to finish. If I take u first and then v, then I'm going indirectly, and clearly this is the shortest path from start to finish. It's going to be shorter than this path plus this path, and that's all that this is saying. Okay, so let's think about the proof of this fact. It seems obvious on the face of it, but we do need a mathematical proof. And we're going to use the algebra of dot products that we've defined. Okay. All right, so first of all, we start with this inequality, and we're going to write down a chain of equivalent statements. So this is the inequality we started with. Now both of these numbers are positive. So this will be less than or equal to this if and only if the square of this is less than or equal to the square of that. So let's run with that. I took the squares of both sides of the equations. Remember that the length squared of the sum of 2 vectors is just the dot product of the 2 vectors. So this side here is equivalent to this side. This side here is just the square of the sum of two numbers, so I can factor this out using FOIL. So the important point here is that this statement here is equivalent to the triangle inequality, and this statement here is also equivalent to this statement here. So if I can prove this statement, I can work my way back and say, okay, if this statement's true, then this statement's true. If this statement's true, then the triangle inequality is true. So that's what we're going to do in this proof, is write down a whole bunch of equivalent statements. Then we're going to get somewhere where we have something that's true, and once we get something that's true, we say, well, since this is true, all of the equivalent statements that we've written down are also true. Okay, so the statement we want to prove is equivalent to this. This statement is equivalent to this statement. Now here I've just factored out the left-hand side. We can use the distributive property for dot product, just like we use the distributive property for multiplication. Okay. On this side, we've just used the fact that the length squared of a vector is the dot product of the vector with itself. Okay. So again, we have a statement here which is equivalent to the statement that we want to prove. And if we cancel out the common terms here, the u.u on the left and on the right, and the v.v on the left and on the right, I end up with this equation. You may recognize this as the Cauchy-Schwarz inequality, which is another famous inequality. But what we've shown so far is that the triangle inequality is exactly equivalent to this inequality here. If I prove this, I can work my way back and get the triangle inequality. All right, so I want to focus on proving this fact here. Okay. And by the way, this is a general proof strategy. If you want to prove something, you try to show that that equation you want to prove is equivalent to another equation that's simpler, and then try to prove that simpler equation. So that's what we're going to do. We're going to focus our attention on this equation here. Okay. So how can we show this equation is true? What we're going to do is multiply both sides by the length of u times the length of v. Again, if u and v are not zero, then these are non-negative numbers. Now, if I multiply this side by the length of u times the length of v, I can rearrange that to come up with an expression like this. You can check that this left-hand side is just equal to length of u times length of v times the left-hand side here. Now, to maintain my inequality, I need to multiply the right-hand side also by length of u times length of v. So that takes this right-hand side over here. All right, again, if I can prove this, I can go back and prove my original statement. All right, so we're going to rearrange this once more. You can see that I have two copies of u squared v squared. I'm going to bring these two copies over to the left-hand side, and I'm going to write them separately. So this u squared v squared is one of the copies from here. I'm sorry. I actually moved this part over to the right-hand side. I'll say that again. I moved this part over to the right-hand side, and I divided this term up into two subterms. Each subterm is u squared v squared. Okay, so I can say that this here comes from here. This here also comes from here. And this term here comes from moving this left-hand side over to the right. All right. Now, if you can, this seems like kind of magic, but you can show that, you can verify that this equation on the right-hand side is simply equal to this expression here. And this is the dot product of a vector with itself. That's the length of this vector. The length of this vector is certainly greater than or equal to 0. So we have our result. We have a result that the length of u plus v is less than or equal to length of u plus length of v. It seems very involved, and it is. This inequality was proven I'm not sure, in the 1700s, after many, many years of mathematics. It is a very beautiful proof, and I invite you to look it over again and try to understand the techniques involved here. Okay. So here we just wrap up the description. As for equality, it holds when and only when this final vector that I obtained here, if this vector here turns out to be 0, if this vector here turns out to be 0, then I have 0 on the right hand side, and that gives me equality here, and I can work my way back to have equalities in all of the statements in my chain of reasoning. Okay. So the only way that this can be equality is if one vector is a non-negative real scalar multiple of the other. Okay. All right. All right, so here, this is a corollary. This was, as I mentioned, this was one of the steps, intermediate steps in the proof. So once we've proven the triangle inequality, we have the Cauchy-Schwarz inequality for free. Okay, so I'm not going to talk about that. Okay, definition of angle. The angle between two vectors is defined as the arc cosine of u dot v over length of u times length of v. Of course, you may be more familiar with the form where you say cosine of theta equals u dot v over length of u times length of v, but it's an equivalent statement. Okay, and you can prove that this agrees with the usual notion of cosine when you take vectors in 2 or 3 dimensions. Okay, so let's do that here. So let's consider the triangle formed by uv and u minus v. Of course, u minus v is the vector that goes from here over to here. And apply the law of cosines. This is just so here's my u minus v, and here's my u, and here's my v. And here's my theta here that I'm looking at. Now, if we write the left-hand side out in components, recall that when we define the length squared of a vector, that's just the sum of the squares of the components. Okay, so this here is the same as the left-hand side here. So I can rewrite this expression. I'm just expanding out all of these squares, and I get 3 expressions like this. On the other hand, if I work on the right-hand side, I can do the very same thing. I can write this length squared as the sum of the squares of components of u. I can write this length squared as the sum of squares of components of v. And I'll just leave this the same. Now, if you compare algebraically this expansion of the left-hand side with this expansion of the right-hand side, you're going to get a whole lot of cancellation. All of the squares go away. That goes with that. That goes with that. That goes with that. And all of the v squareds go away. v1 goes with that. v2 goes with that. v3 goes with that. And if you clear away the smoke, you'll see that what you have on the left-hand side is minus 2 times u1 v1 plus u2 v2 plus u3 v3. And on the right-hand side, you have minus 2 times this here. And we get the familiar formula that we saw up here. Cosine theta is u dot v over length of u times length of v. So all that went to show that this definition of cosine, which is true in arbitrary number of dimensions, agrees with our usual concept of cosine in 2 or 3 dimensions. Okay. All right. So vectors from Rn are orthogonal, that is perpendicular, if and only if their dot product is 0. Okay. What does perpendicular mean? It means the angle between them is 90 degrees or pi over 2. And what is cosine pi over 2? Cosine pi over 2 is 0. Okay. And when is the cosine going to be 0? When the dot product is 0. Okay. And two vectors are parallel if and only if their dot product equals the product of their lengths. Similarly, if two vectors are parallel, what's the cosine between them? Cosine is 1. You can follow through that reasoning to show that the dot product must equal the product of the lengths. Okay, that's it.